This last function that we need is going to be kind of strange. Some of you may have seen it, some of you may not have seen it. So we'll just go over how this thing is defined, what it looks like, and some of its properties. It's the greatest integer function. The textbook uses int of x to denote that. I like this one, x with almost these square brackets, except it's only the bottom part that is included. It's not the top part like a regular bracket would be. And to define it is it's the greatest integer that is less than or equal to x. It sometimes helps to have a number line set up just to get a sense of where everything is living. Now I'm just going to find where 3.2 is. It's 3. So 3.2 is right here. The integer that is less than 3.2, but is the largest of all integers that are less than 3.2 is 3. If I looked for negative 1.2, that is over here. And so I'm only going to be looking for integers to the left of negative 1.2, and the first one I come up to is negative 2. And if I look at 0.9 repeated for a little bit, blah, blah, blah. Right, let's just say that that is that. And I'm only looking to the left, then the closest or the first integer we come across is 0. An alternative definition that kind of wraps it up nice and neat is the greatest integer of x is equal to this integer n if it satisfies this rule right here, that when you do x minus n, 0 is less than or equal to that, which this is then less than 1. So you land inside of a small interval. If we looked at this, let's see if that works. So we have 3.2 minus 3, which gives us 0.2. 0.2 is between 0 and 1. That's a good one. So that tells us this works. If you chose any other integer, you would not land between 0 and 1. If we take negative 1.2, subtract off negative 2, we have double negatives, so that's really negative 1.2 plus 2, which gives us 0.8. 0.8 is between 0 and 1, so we're good to go. And then if you did the same sort of thing here, since 0.9 is between 0 and 1 already, well, you just take 0, because that's what you would have to subtract off to stay between 0 and 1. Now, every number has an integer that is less than it, which means our domain is all real numbers. We'll come back to the range once we graph this. So if I take any number between 0 and 1, but not equal to 1, it is already inside of this interval here. And so any number there stays at 0, just like this stayed at 0. If I was to take a number between 1 and 2, but less than 2, the next integer to the left of it is going to be 1. And so we end up with another step right here. And if we were to take a number between 2 and 3, like 2.5 or 2.7, then looking only to the left, the first integer that we hit is 2. And so we get another kind of barbell thing here. And this just keeps going and going and going. And then to this side, if you take a number between negative 1 and 0, well, just like we did over here, if you look only to the left, you're going to first hit negative 1. Then same thing over here, and so on. So you get this infinite stairwell, I guess, or staircase. And if we took this graph and squeezed it down so it was right on top of the y-axis, the only outputs that we're getting are integers. So that's really strange, is that we're only getting things that are separated by at least one full step in either direction. Our x-intercept, well, everything that's between 0 and 1 lands on the x-axis. So we have a whole bunch of numbers between 0 and 1 that are x-intercepts. Our y-intercept is smack dab right at 0. Our symmetry, this is gonna sound kind of weird, but there is none. Even though you can kind of imagine spinning it, if you spin it, it still doesn't land correctly. Where's it decreasing? Nowhere. Where's it increasing? Also nowhere. I know that seems kind of strange because you see that there's a jump here, but there's a jump here because this has to be a function, and there's nothing in this open circle. There is something here. So there are no local max, no local min. I guess we were using NA instead. And there's no absolutes either. Strange function, kind of neat. And it does have some applications in the real world. So the next thing we need to do is define functions that have different definitions on different parts of their domain. So when a function is defined by different equations on different parts of its domain, it is called a piecewise defined function. Right, for instance, this is an example of a piecewise defined function. When x is negative, your function looks like x squared. When x is positive, your function looks like x plus 1. When x is equal to 0, it just gives you the number 2. And so let's play around with this. We want to find out what f of negative 2 is. Negative 2, come over here. It is less than 0, so that means we're on this part of the function. And so our function looks like x squared. All right, and negative 2 times negative 2 gives us 4. So f of negative 2 is 4. We can come over here and plot that if we wanted to, but we'll talk about how to graph these a little bit easier than just plotting a bunch of points. F of 0, 0 is 0. And so our function is equal to 2. And then f of 3, 3 is larger than 0, which means our function tells us to do x plus 1, which gives us 4. Next, we need to determine the domain of the function f. And so we have all negative numbers covered, we have 0 covered, and we have all positive numbers covered, which means our domain is all real numbers. And next, we want to graph this thing. So I'm going to talk about how to graph this somewhat easily. What we're going to do is everywhere where we change definitions, I'm going to make just a dotted line, vertical line, to indicate that things are going to change. Now, from negative infinity all the way to 0, our function looks like x squared. So as we saw earlier, we know what x squared looks like. It's going to look like half a parabola because we have to stop at 0. And now we can't plug 0 in to this over here. So we're going to use an open to indicate that 0 is not included in this definition of the function. But when we do have 0, the output is going to be positive 2. And then once we pass 0 and we keep moving in the positive direction, our function looks like x plus 1, which is a line starting right around here. Right? We need an open 1 because, again, 0 is not included. And we know what x plus 1 looks like. It's a line with a slope of 1 and a y-intercept of 1. but we don't include that y-intercept. So that's the graph of this piecewise defined function. Let's use the graph to determine the range of this function. So again, if we take this and just squeeze it down on top of the y-axis, we need to figure out what is covered up and what isn't. So we have everything from almost 0 to infinity being covered up by this kind of portion of a parabola over here. And anything that's coming from either this dot or this line will also cover up parts of what this will cover up. And so we're missing 0 and all negative numbers, which means we go from 0 to infinity, right, up that way, and we don't include 0. That is our range. Now we need to figure out if this thing is continuous or not, and so we just start up here and we try to trace it and see if we pick up our pencil or pen while we do it. So we're just trucking along, we're going. We hit here, have to jump back, and then keep going. So we actually had 2 jumps, so this thing is not continuous. We got a couple breaks. We'll try this one out down here. So we have a starting of -3. I'm gonna indicate that with this dotted vertical line. We have something going on at x equals 0, right here. We have something going on at x equals 1. And then everything else is good. So we need to pay attention to what happens here, here, and here, because things going to change. So between -3 and 0, we're going to have a function that looks like -2x plus 1, which is aligned with a slope of -2 and a y-intercept of +1. So if this was a line that we were graphing, we go all the way up to where the y-intercept would be, because that gives us a free point, and then the slope was -2. So your rise is +2, your step is 1 back. So this thing, let's see, what do we get if we plugged in -3? So f of -3 is -2, -3 plus 1. And so that gives us +6 plus 1, giving us 7. All right, so that's going to be somewhere up here. And notice I'm not drawing arrows on this because we stop at -3. Now, from 0 to 1, whatever you plug in between 0 and 1 always gives you 1 back, including when you plug in 0. So that's going to fill this dot in. And then all the way out to +1, we get just the number 1. And now from 1 out to infinity, so over here, our function looks like x squared. So this would be technically an open circle. And when you plug in 2, you get 4. This thing just keeps going and going up like that. I kind of skipped to part 3. Let's dive back into part 1. So we want to find f of -2. Well, -2 is between -3 and 0. So we take -2 times -2 plus 1, because that's what our function looks like between -3 and 0. That gives us 4 plus 1, which gives us 5. If I take f of 1, well, 1 is equal to 1. And our function says anything between 0 and 1 gives us 1 back. And then f of 2, well, 2 is larger than 1. And so our function looks like x squared. And 2 squared gives us 4. We want to determine the domain of f. We don't have anything graphed to the left of -3. So this is a filled in dot. But to the right of 1, this just keeps going. So we have an arrow, which means our domain is going to be -3 out to infinity. All right, make sure that that makes sense to you. We don't know what's happening to the left of -3. It's not defined. Nobody tells us what's going on. And so we have to stop at -3. We already took care of step 3. Very good. We're going to use this graph to determine the range. So again, squeeze it down, or imagine squeezing down this graph just onto the y-axis. And here we're covering up from 1 to 7, just this segment right here. This segment right here just collapses down onto 1. And then this, since it keeps growing and growing and growing, is just going to blow up to infinity. So with that in mind, we only have values on the y-axis from +1 out to infinity. Next, we want to find out if f is continuous on its domain. Well, we're starting up here at the leftmost point of its domain, dropping down, still haven't picked up the pencil. We hit this turn, it's quite sharp, but don't pick up our pencil. Hit this other turn, and then we're smooth sailing from here on out. That just keeps going, never picking up your pencil. So since we can trace it without lifting our pencil, we have yes. This is continuous on its domain.